We are solving a very interesting AIPMT 2012 question. It's in laws of motion. It's a part of collisions, like a two-dimensional collision. The problem is like this. Two spheres A and B of mass m1 and m2 respectively collide at an angle. A is initially at rest and B is moving along V along x-axis, right? After collision, B has a velocity v by 2 in the direction perpendicular to the original direction. Mass of A moves after the collision. In what direction is the question that's been asked? Let's try to draw a diagram and try to understand what is given for you. It is being said that A, whose mass is m1, is initially in the state of rest, u1 equal to 0. B, whose mass is m2, is initially moving with a velocity he has given it along x-axis. This go and collide at this. And it is further given that after the collision, B has a velocity v by 2 in a direction perpendicular to its original direction. That means what? This B, this is A. B has moved perpendicularly this way. This is how B has moved, whose mass is m2. The velocity v by 2, but is perpendicular to its initial motion this way. Then how does the A is moving? That's the question, right? So A obviously cannot move this way. Rather, as per the basic observation of conservation, it shall be, we don't know exactly, but we don't know exactly how A is moving, but assume A is moving by making an angle theta with the x-axis in a downward direction. If my assumption is wrong, I will get obviously theta equal to 0. That shall not be a worrying aspect, right? So I can resolve this maybe moving with a velocity v, or else we call it like x, moving with a velocity x. That's what we are supposed to find out. Now, I need not find out, actually finding a direction is sufficient. Or else let me call Vx so that it becomes easy. This Vx is in this direction, which can be resolved into components as Vx cos theta and Vx sin theta. So I have now velocity is just divided in all directions. I can apply conservation of momentum, right? Let's apply conservation of linear momentum along x direction first. Along x direction. Initially, the first one is in the state of rest. So m1, conservation of linear momentum, you know the formula, na? m1 u1 plus m2 u2. Momentum before the collision is momentum after the collision, m2 v2. The second body, m2b, is having a velocity v along x-axis as it is given in the problem. After the collision, the first body m1 is having a velocity vx cos theta. I don't know that's value. But the second body m2 is having velocity only along y direction. So m2 velocity along the second direction equal to 0. So you got an equation here. What is that equation I have got? m2v equal to m1 vx cos theta, and this is also equal to 0. We call this as equation number 1. And let's apply conservation of angular momentum, linear momentum along y direction before and after the collision. See, before the collision, the first one is in the state of rest. So m1 into 0. m2 into it is given that the second one is moving along x-axis initially. So no momentum along y-axis. After the collision, the first one is coming down. So if this is plus j, this has to be treated like minus j. So what we can say is the initial momentum of the first body is minus m1 vx sine theta, right? J cap, we can say it is required. I need not write because I'm already talking about y-axis. I need not write a j cap actually. I can eliminate this j cap sine theta. And how about this one? m2 3 by 2. I have written this as minus because this is downward. This as plus because this is upward. Left hand side is 0. This minus on the other side becomes a plus. Therefore, what we can say, m2 v by 2 equal to m1 vx sine theta, where vx is the velocity of first body after collision, not a part of it, but a complete velocity. Now you see this equation number 1 and 2. One is having cos theta, one is having sin theta. Let's make 2 by 1 and see what it gives. 2 is m2 v by 2 on the LHS side. On the LHS side of the first equation, m2 v. LHS side of the second equation is m1 vx sin theta. LHS side of the first equation is m1 vx cos theta. m1 vx can be cancelled on both sides, m2 can be cancelled, v can be cancelled. So 1 by 2 equal to tan theta, or theta equal to tan inverse of 1 by 2 is the answer for the problem. That is this one, option number C, tan inverse of 1 by 2 to the x-axis. But be careful to understand that this is not above the x-axis, but it is below the x-axis. That is in clockwise direction. But I need not mention that because that kind of options are not there. So while you are solving this problem, during the journey of this problem, we have explained a very important concept. That is conservation of momentum. That when no external force is acting, momentum of a system before the collision is after the collision. As there is a possibility of two-dimensional motion, I have conserved the momentum along x direction as well as conserved the momentum along y direction separately and simplified that. By substituting this value of the theta, I can get the value of that Vx2 if needed, but it's not required in this problem. That's how we solve this problem. Thank you for watching.